In this section, which is section 10, we're going to be looking at the reactions of esters. So we can hydrolyze esters with water in the presence of an acid or a base. We're going to look at the acid first, but we can hydrolyze it in the presence of an acid to give us a carboxylic acid and an alcohol. And the alcohol is whatever the alkoxy group is that makes up the ester. That's going to be our alcohol. And of course, the acid is going to come from the carbonyl component. We can also react esters with ammonia or amines to form either primary, secondary, or tertiary amines. And so here we've got an amine reacts with the ester. If we start with ammonia, we'll get a primary amine. If we start with a primary amide, if we start with a primary amine, we'll get a secondary amide. And if we start with a secondary amine, we'll get a tertiary amide. So acid-catalyzed, we're going to look at the mechanism of acid-catalyzed hydrolysis. And this is very similar to the Fischer esterification mechanism that we did in the previous video. What's different is here we're going the opposite direction. That's essentially the difference. So it is a six-step mechanism, and as with anything that is acid-catalyzed, we usually start with protonating our carbonyl. So we're going to protonate the carbonyl. That will give us a resonance-stabilized carbocation. That will increase the partial positive charge on this carbon, which will allow for nucleophilic attack of water on that carbon. That will give us this protonated intermediate, and so we will need to deprotonate. So we'll do the deprotonation of the intermediate, and then we're immediately going to protonate the OR group. And so we had the same intermediate when we were looking at the Fischer esterification. We had this exact same intermediate, except there we protonated one of the OHs. Well, here we're protonating the alkoxy group. Once we protonate that, we will now eliminate an alcohol, and that will give us a resonance-stabilized carbocation. We don't have the other resonance structure here. And then we deprotonate that one of the OHs, and that will give us our carboxylic acid. So the result of this is that it gives us a carboxylic acid and an alcohol. So we're going to look at number 47, which I have right here. And with this, we've got this. So the gamma butyrolactone, which is this, is biologically inactive. If it's converted into, it is converted in the body to 4-hydroxybutanoic acid, which is this, which is also called GHB, and this is a dangerous drug. I'm going to show you how the hydrolysis of this particular ester to this dangerous drug, how that works. So the first thing, we're going to take this and we're going to protonate it with our acid. And I'm just going to put the HOH2 plus. And so we'll protonate that. We will need some lone pair electrons on that. And we'll take that lone pair electrons and go to the hydrogen. And then we'll kick those electrons back to the oxygen. All right, at that point, we now have a protonated species. That protonated species will have a resonance structure. So I'll go ahead and draw both of those. All right, so we did have 2 pair of electrons there. And so there's still 1 pair of electrons left. And this has a positive charge, and we have H2O. All right, that H2O will come into play here. H2O, lone pair electrons. Now, I'm going to go ahead and draw the resonance structure here because that resonance structure helps us to realize that there is a partial positive charge on this carbon. So if we take that pair of electrons that is the pi bond and we kick it out to the oxygen, we will get a positive charge there, OH. All right, and we'll have that. All right, well, that is what we're going to attack with our water nucleophile. So we're going to attack with water, the nucleophile, and that will give us this. And when that gives us this, and I'm actually going to draw this a little bit differently. So let me erase those hydrogens. I'm going to draw this differently because we're going to deprotonate this, and it's easier to do if we have the hydrogens specifically drawn. All right, so we are now going to deprotonate this with a water molecule. So there are lots of water molecules just floating around in solution. So we'll take an H2O, and we're going to deprotonate this, and then keep those electrons over there. All right, and so at this point we've got a neutral molecule, and we're now going to protonate the oxygen that is on the ester, or that oxygen there. So we'll protonate that, HOH2 plus. We'll use one of these electrons, one of those pairs of electrons, to deprotonate the H3O plus. All right, and when we do that, we're going to end up with a protonated species. There's still a pair of electrons there, but this has a positive charge. So at this point, we're going to break this carbon-oxygen bond. So we're going to kick that pair of electrons over to the oxygen, and that's going to put a positive charge on this carbon. All right, and just so we're clear that we have the proper number of carbons. So this carbon here is the 1, and then we'll have 2. So this is the alpha, beta, gamma carbon, alpha, beta, gamma, and the gamma is the one with the OH. All right, and so now we're going to take this pair of electrons and share them in to make a pi bond. And we're very close at this point to our final structure. Go. All right, and our last thing we need to do to get from here to our GHB is simply to deprotonate with an H2O molecule. And we'll just put that onto the oxygen. I'm going to draw that one a little bit more clearly. I got a little sloppy there. So we'll take this pair of electrons and we'll go to that oxygen. All right, and that's going to give us this as our final product. So just to review this particular mechanism, protonate, we can draw our resonance structure. So protonate, attack with our water nucleophile, deprotonate, protonate, leaving group, and then this has a resonance structure. And I really should have put this like this because that's a resonance structure. So these are resonance structures of each other, and then deprotonate. So protonate, attack with the nucleophile, deprotonate, protonate, leaving group, deprotonate. And that gives us our total mechanism. So protonate, nucleophile, deprotonate. Protonate, elimination, deprotonate. If we go back over to our thing, there are the same 6 steps. Protonate, attack with nucleophile, deprotonate. Protonate, elimination, deprotonate. And that gives us our hydrolyzed ester. That gives us our hydrolyzed ester. Now, we can do base promoted, and you'll notice I'm using the word promoted here, base promoted ester hydrolysis mechanism. The reason we don't call it base catalyzed is because hydroxide is not regenerated in the course of this process. So this is a 3-step mechanism. The first step is that we attack with hydroxy group. That will give us our tetrahedral intermediate that we have seen now many, many times. And at this point, our OR will be lost, so we'll lose the alkoxide group, and that will give us our carboxylic acid. Since this is still a very basic solution, we will deprotonate with, they'll deprotonate the OH on the carboxylic acid, and that will give us a carboxylate. So it'll give us the conjugate base of our acid. You'll see here that hydroxide is not reproduced in the course of this reaction, so this is not base catalyzed, it is base promoted. You do need to have a stoichiometric quantity of hydroxide for this reaction to work. All right, we're going to look at lipid hydrolysis. Now, many schools for the organic lab, one of the experiments they like to do is to make soap, and you can do that by lipid hydrolysis with base. And so you can take an ester, which is a triacylglycerol. All right, so you can take this triacylglycerol, and this is a fat that you could find either in vegetable oils or even in animal fat. The main difference between the animal fat and the vegetable oils is that most of the vegetable oils, the R groups, have several cis double bonds in them, and most of the animal fats, for most of the R groups on the animal fats, they are saturated, and that's like a big difference between them. All right, so we have these triesters. They have these long hydrocarbon side chains. And those long hydrocarbon side chains in the animal fats, they are saturated, but in the vegetable oils, they're mostly unsaturated. Although there are some vegetables and plant products that have saturated fats. Most of them have some sort of unsaturation on them. So it looks like this. It's a big molecule. It's very greasy because there's just little tiny bits of polar stuff here, and that's not enough for this to dissolve in water. So we'll generally find that this is completely insoluble in water. So we can take this and do base hydrolysis, that mechanism we just looked at. We can do base hydrolysis on this, and when we do, we can create the fatty acids. Now, in your body doesn't use base hydrolysis. We don't have sodium hydroxide or potassium hydroxide sitting around in our gut. Instead, it uses enzymes, and the particular enzyme here is the lipase. It will use the enzymes to hydrolyze this and give us 3 fatty acids and glycerol. And so that's how it is carried out in our bodies. When we're doing this in the lab, though, we can use sodium hydroxide. And as I mentioned, we cannot use the sodium hydroxide inside our bodies. That would be a big disaster. One interesting thing. Okay, so I'm going to go back here. Here is a picture of an oil, and this could be either a vegetable oil or an animal fat. Again, the big difference is how many unsaturations it has. All right, and here, this is a fake fat. So this is where we've got this sucrose that has been functionalized with acyl groups. So we've converted this sucrose into acyl groups. And all of the R groups are, from 11 to 19 carbon, so you can use fatty acids that you normally would use. And so we've completely turned this into an ester. And so all of the components of this are natural components. So there's nothing like, really weird on it, except that this thing would never form in nature. So you can take sucrose and convert it to this thing, which was called Olestra. It still is, it's still called Olestra. And it makes a big fatty molecule that when you eat it, it gives the texture and feel of eating an oil. And so, and since most oil compounds, fats in foods are generally very satisfying. And so this has a very satisfying feel to it. I have heard, I have not tested this, I've not tried it. This was approved as a fat substitute back in the 1990s. And it was popular for a little bit, but it kind of fell out of favor due to some issues. So, the main issue is that it caused some unpleasant side effects where because the whole idea behind this is that your body doesn't process this fatty molecule, and so it just passes right through your intestines. So instead of your body absorbing all of these fatty acids and converting them into fat in your body, it just passes them right through. Well, what that caused was if you consumed a lot of this, that caused some people to have loose stools. And that was reported in the popular media quite a bit. And so people shied away from it. When you start talking about loose stools, people suddenly lose interest. All right. Now we want to look at saponification. If we have an oil, so here is an oil that we could get again from vegetable or from animal fat. We can hydrolyze it with sodium hydroxide to give glycerol. And instead of getting the fatty acids, we're going to get the conjugate bases of those fatty acids. And these are soap molecules. All right, so again, heating the animal fat with vegetable oil and aqueous base, it hydrolyzes it, and we get these are soap molecules. These soap molecules are very effective at being soap because they have a very polar end where we've got an ionic end component here. This interacts with water really, really, really well. And we've got this nonpolar tail that interacts with oil very, very well, or nonpolar compounds. So when we use soap, we can create soap micelles. Now, I've shown this picture before, way back in chapter 3, when I first talked about soap and this kind of molecule. But the whole point is that these nonpolar components kind of stick into a big droplet of oil, and the polar part on the end is at the surface of that oil. What that does is it lowers the surface energy so that this oil droplet, not so much the oil droplet, but the polar part at the end, can now interact with water. And that allows us to have oil droplets in the water that don't like bump into each other and coagulate and make bigger oil droplets. Instead, they will stay suspended in this mixture. And so those are soap micelles. Now, things that you can do to improve the micelles is that, one, you can warm up the water. If you have warmer water, this happens more easily and it is more effective. And this is part of why we use warm water when we are washing our hands. All right. So we're now going to look at our last section. And in this last section, we are going to do the reactions of amides. So amides happen to have the poorest leaving group of all the carboxylic acid derivatives. They're the least reactive. Really, there's not a whole lot of options to do with them except hydrolysis. And so we can take amides and we can hydrolyze them either with aqueous acid or with aqueous base. If we hydrolyze them with aqueous acid, we will get the carboxylic acid and the protonated amine as products. If we do it with base, we will get the carboxylate anion and the unprotonated amine as products. It does take warm conditions to do this. It's not crazy high temperatures, but you do need to warm it up, and you do need to put strong acid or strong base into solution. So this is not a very mild conditions. This does take quite a bit of doing, but it is something that is definitely possible to do. So if you have an amide and you want to convert it into a carboxylic acid, you can do it. Just remember, you're going to use a hot, strong acid to do it, or hot, strong base to do it. All right, so as far as the base mechanism, we've looked at similar acid type mechanisms, but we're going to look at the base mechanism here. First step, when it's the base, we have nucleophilic attack of the hydroxide ion on the carbonyl. That gives us our ever so familiar tetrahedral intermediate. And then this is the hard part. We're going to have NH2- act as a leaving group. And I have been telling you all throughout organic chemistry, at least many parts of organic chemistry, that this is not a good leaving group. It's not. This is part of why we need very warm conditions, and we need the strong base to make this happen. We need a pretty significant excess of the hydroxide. So we can eliminate that, and when we do eliminate that, we will get the carboxylic acid plus the amide anion, and that can deprotonate the carboxylic acid to give us the carboxylate plus the amine. And so that is our mechanism for base hydrolysis of an amide. All right. Oh, yes, there is this one last section that is kind of cool, or actually two last sections here that are kind of cool. This one is talking about beta-lactam antibiotics. And I just point this out because there are many antibiotics that have this beta-lactam, which, as we know, that is a strained system. Typically, a four-membered ring like this is going to have a bond angle of about 90 degrees. However, these are all this is sp2 hybridized, this oxygen or this carbon here, and these other things are sp3 hybridized. And so for all of those, 90 degrees is quite a bit of angle strain. So one of the things that happens is when the antibiotic interacts with the particular enzyme that is on the bacteria, it causes a reaction between this molecule and the enzyme, which inactivates that enzyme and inactivates the bacteria. And as a consequence, the bacteria doesn't grow. So this is very effective at killing bacteria. Now, it doesn't work for every single bacteria. You can use different antibiotics that work better on different types of bacteria, but it is kind of amazing. For much of human history, there was no real treatment for bacterial infections. If you had a bacterial infection, you just kind of had to, fight it out on your own without antibiotics. And now that we have antibiotics, a lot more people live through bacterial infections. So, all right. So here is a quick summary of the nucleophilic acyl substitution that we have talked about. It's good to organize these, and I think it's very useful to put them all into like a table so you can understand what is going on. That are least reactive are the amides, the carboxylic acids and the esters are more reactive. The anhydride is more reactive than that, and the acid halide or the acid chloride is going to be the most reactive. It's very easy to go from one of these more reactive to one of the less reactive, but it's more difficult to go back the other way. This is why it's so useful to be able to take an amide and hydrolyze it to a carboxylic acid, because you're going back the other way. Or to take a carboxylic acid and convert it into an acid chloride, that's like you're working your way up the ladder. So, all right, I like this table because this table gives us a very quick summary of what reactions we're capable of doing. So you can take these starting materials and turn it into these products if there's a check mark. So acid chlorides, yes, you can turn it into anything. Acid anhydrides, you can turn it into anything except for the acid chloride. Carboxylic acids, these ones are kind of unusual because we had a workaround for all the carboxylic acids. So we could turn it into acid chloride with thionyl chloride. There are some acid anhydrides we can do. So this one's maybe a check with a star by it or something. Esters, we can do Fischer esterification, and then this, either DCC coupling, or we could do just the really high heat with an amine. Esters, we can turn them back into the carboxylic acid with hydrolysis, or we can turn them into the amide using an amine. And then finally, the amides, really the only reaction we can do is hydrolysis to get it back to a carboxylic acid. But once you have a carboxylic acid, you always have the option of going back and making an acid chloride. So that means that it's possible to go back, but we have to do some tricks. Let's look at number 60 on the in-class assignment. So we're trying to figure out what reaction can we use to start with, oh, I need to switch over here. To start with benzoic acid all right, so we want to start with benzoic acid and then make these particular components. For some of these, there's more than one pathway. So there's more than one pathway, but I'm going to start with sort of the obvious pathway for each of these. So for this one, I'm going to start with, I'm going to start with the benzoic acid. All right, and we can convert that benzoic acid into the acid chloride with thionyl chloride. All right, and then with the acid chloride, we can convert that into this compound directly by using the isopropyl organocuprate. So in step 1, we could use the so CH3 2CH 2 copper lithium reagent. So this is just the diisopropyl copper organocuprate. All right, and then 2 H2O, and that would give us this particular product. So that's pretty easy. All right, on this one, this is an acetal. And in order to do an acetal, we need to convert our carboxylic acid into an aldehyde. And so here, we need to convert that carboxylic acid into an aldehyde. That is not, we can't do that directly. There are several pathways that we can use to do this. One, we could convert our carboxylic acid into an ester and then use dibial to get the aldehyde. I'll go ahead and do that one. All right, so we'll use our carboxylic acid, convert that into an ester. So we'll use CH3OH, and we'll use toluene sulfonic acid. All right, and that will give us an ester. So this CH3. And then we can use dibial in step 2, H2O, and then that will give us an aldehyde. All right, and then once we have that aldehyde, we can convert that aldehyde. I'll go ahead and put it here. Once we have that aldehyde, we can convert that into this acetal by using our ethylene glycol, which is that 1,2-diol, And then again, we'll use the toluene sulfonic acid as an acid catalyst, and that will make this particular acetal. So that'll make the product there. All right, so next one. Again, we're going to start with our carboxylic acid. And we're going to convert that carboxylic acid into an amide directly using the brute force technique. And that brute force technique is where we lock it in a chamber with ammonia and heat the snot out of it to over 100 degrees Celsius. And this amine's pretty volatile. This may be kind of tricky, but we should be able to do it and get this amide. All right, that amide, in turn, we could convert into an amine because we want to get rid of that carbonyl. We could convert that into amine using step 1, the lithium aluminum hydride and water, and that will give us this amine. And then we can treat that amine with, here we just need the acetyl chloride, so CH3COCl. We treat that with that. And all right, here's the downside of this. It's that it's going to take 2 equivalents of this with this acetyl chloride in order to make, yes, it's going to take 2 equivalents of this with the acetyl chloride in order to make our ester. So that definitely has its downside. All right. Oh, wrong carbonyl. So NH carbonyl. Now, there is an alternative that doesn't require us to use 2 equivalents of this. And that alternative is to use the CH3 CH3 COOH, which is just acetic acid, and DCC to do a DCC coupling, and that will give us this this acetyl compound. All right, final one. We're going to take the acid chloride that we had made earlier all the way up here. So we're going to use that as our starting point. All right. Although we could choose an ester here as well, but we can use that as our starting point. And with that, we could do CH3. I wanted to make this. Let's start over here. Step 1, use CH3, and how many? 1, 2, 3 carbons. So CH3, CH2, CH2, MgBr, and we'll use 2 equivalents. And in step 2, we'll use H2O, and that will give us our product. It'll give us this product. All right. Like I said, you could use the ester instead of using the carboxylic acid. So you could take that carboxylic acid, convert it into like methyl ester, and then put that in place here, and you would get the same product. So either one of those would work. Important thing is that there's more than one possibility for doing this. All right, so there's just a little bit of stuff that we're going to use to wrap up this. I'm going to talk a little bit about natural and synthetic fibers, polymers. So natural fibers are, they can be either plant or animal sources. So like wool and silk are just very long proteins. So like hair is a protein. So it's made up of all these amide bonds, and those amide bonds, peptide bonds, make for a fairly strong molecule. You also get things like cotton and linen. They're derived from carbohydrates. And so they're like carbohydrates that are in cellulose, and those tend to have these big long chains. They're polysaccharides essentially. All right. When it comes to synthetic fibers, there are a lot of options that we can use, and one type are called condensation polymers, and the most common one of these is nylon. And so nylon is a condensation polymer. I would say it's probably the most well known. I don't know that it's the most common now. Probably the most common polymer that you run into now that's a condensation polymer is probably going to be polyethylene terephthalate. It's what all the plastic water bottles and soda bottles are made out of. But so nylon 66 is this component. The reason we call it nylon 66 is that we have a diamine that has 6 carbons, and we have a dichloride that also has 6 carbons. So diacid chloride that has 6 carbons. And when we mix those together, we'll make new bonds between these nitrogens and here, and so we'll make these new amide bonds, and we'll make these very long chains. We will get some hydrochloric acid, but we can put some other stuff in there to soak up that hydrochloric acid, and we can get these nylon. There's some other ways to do it that involve not having to make the acid chloride. Like, for example, you could take this and the diacid instead of the diacid chloride and just heat it up to a very high temperature. And that is how some of these are made. But in all of the cases, when we do these things that are called condensation polymers, we eliminate a small molecule. And the small molecule in this case is HCl. If we had started with the carboxylic acid, the small molecule would have been water. All right, so here, this one is polyethylene terephthalate, so PET. And when you heard that earlier, is that how you thought terephthalate was spelled? Well, it is. That's how terephthalate is spelled. So here is terephthalic acid, and this one's the para-terephthalic acid. And when you use a catalyst, an acid catalyst, you can do essentially a big Fischer esterification. With ethylene glycol, you'll drive off water. So if you heat it up, you'll drive off that water. And you will get this very long condensation polymer. All right, and again, this is essentially a Fischer esterification. All right. This particular polymer is a huge volume polymer. It's used throughout the world. This is used in making of polyethylene terephthalate or PET bottles. But it comes under a lot of names, and there's a lot of variations on it, like how big you make this will affect some of its properties. Polymer chemistry like this, it's a whole field of chemistry, and so there are many different variations that you can do with this reaction to change the properties. And so that is that. Like mixing in a little bit of a different glycol. Instead of ethylene glycol, throw in propylene glycol and see what happens. And you'll see that it will change the properties of that polymer a little bit. So huge range of possibilities for these polymers.